Section: Introduction. In this section, we discuss the significant advancements in machine learning over the past 5 years, particularly the success of transformer models in various fields like natural language processing, computer vision, and geometric deep learning. However, we note that traditional transformers have high time and memory complexity, which poses challenges for efficiency. To address this, we explore methods to make transformers more efficient, particularly by reducing the attention mechanism's complexity. For example, Big Bird uses a sparse attention mechanism for sequential data, while Spexphormer does the same for graph data by creating a sparse interaction graph. Spexphormer reduces the complexity of each layer significantly, but training remains memory-intensive, especially for larger graphs. We aim to enhance the scalability of efficient graph transformers like Spexphormer. One common strategy is to use batching techniques, such as egocentric subgraphs and random node subsets. However, these methods can be costly and may not retain important edges. We also highlight the limitations of random neighbor sampling methods, which can overlook critical connections in expander augmented graphs. To improve scalability, we propose training a smaller network to identify significant edges, which can help us reduce the complexity of the larger model. We find that attention scores from the smaller network are consistent with those from a larger network, allowing us to use these scores to sparsify the graph effectively. Our approach involves training a small width network to estimate attention scores, which we then use to create a sparse graph for a larger network. This process reduces the complexity of Spexphormer and allows us to train the initial model on a CPU, making it more practical. We then use the attention scores as edge features for the larger network, further reducing complexity. We introduce a unique sparsification method that combines expander edges, self-loops, and graph edges, varying the attention pattern across layers. This method improves computational efficiency and allows for effective batching of large graphs, enabling us to model long-range dependencies. Finally, we utilize reservoir sampling for efficient edge sampling, enhancing the speed of our model. Our contributions include analyzing the similarity of attention scores across different network widths, proposing layer-wise sparsification based on learned attention scores, and developing a two-phase training process that reduces memory consumption while maintaining accuracy. Section Summary. In this section, we discuss the success of transformer models and the challenges of their high time and memory complexity, particularly in graph data. We propose a two-phase training approach that utilizes a smaller network to identify significant edges, allowing for layer-wise sparsification and reduced complexity, ultimately enabling the scaling of transformers to larger datasets while maintaining competitive accuracy. Section: Related work. In this section, we discuss related work on graph transformer architectures. We note that attention mechanisms were introduced in early graph neural networks, like graph attention networks, which help nodes aggregate information from their neighbors without positional encodings. GraphBERT focuses on node encodings based on the graph structure. Later developments led to full graph transformer models that extend beyond simple message passing, including spectral attention networks, Graphormer, and Graphit. Graph GPS merges attention with message passing, combining the strengths of both approaches. We also highlight efficient graph transformers, where recent studies have proposed scalable architectures. For instance, NAGP-Hormer and GoFormer utilize sampling methods, while Difformer introduces a continuous time diffusion-based model. Spexphormer creates a sparse graph that merges the input graph with an expander graph and virtual nodes, demonstrating improved performance over other sparse transformer methods. NodeFormer, inspired by Performer, employs the Gumbel softmax operator for efficient information propagation among nodes. SGFormer shows that a single-layer transformer can enhance results from GCN-based networks while maintaining a low memory footprint, making it suitable for large networks. SkeinFormer is conceptually similar to our work, as it uses sketching techniques to speed up self-attention. We also address sampling and batching techniques that help manage the neighborhood explosion problem. For example, GraphSage samples a fixed-size neighborhood during node aggregation, and GraphSaint scales GCNs by sampling the training graph to create mini batches. Next, we introduce Spexphormer, which employs an expander-based sparse attention mechanism for graph transformers, requiring linear computation based on the number of vertices and edges in the input graph. Spexphormer constructs an interaction graph that includes edges from the input graph, an overlaid expander graph, and virtual nodes connected to all original nodes. The expander graph uses a constant degree random structure, allowing information to flow between distant nodes without needing direct connections. This design helps avoid information bottlenecks. In our model, we denote the attention pattern as H and the neighbors of a node I as n_H, I. We represent the matrix of d-dimensional embeddings for n nodes as X. Our main focus is on H-head attention, where we perform element-wise multiplication and apply linear mappings to node and edge features. Spexphormer incorporates learnable edge features for different edge types, enhancing the model's ability to differentiate attention edges. We use the ReLU activation function, and in cases without original edge features, we simplify the computation of edge features, reducing complexity. We introduce B_J to provide a straightforward way for the model to adjust the importance of various edge types. By treating Spexphormer as a bridge between message-passing neural networks and full transformers, B_J allows attention scores for non-graph edges to approach 0 without hindering performance on graph edges. We ensure that each layer outputs features of the same width as its input, maintaining consistency in our parameter matrices. We compare our network to Spexphormer, which serves as our base model due to its flexibility in adjusting attention graph sparsity and modeling long-range dependencies. Our implementation of Spexphormer includes self-loops for every node and utilizes random Hamiltonian cycles to create the expander graph, while we do not incorporate virtual nodes. Despite this, our network remains a universal approximator. Although the best results for Spexphormer combine sparse attention with message passing, we focus on scalability by avoiding the MPNN component and making additional adjustments as detailed in our paper. Section Summary. In this section, we review various graph transformer architectures that utilize attention mechanisms, highlighting models like Spexphormer, which employs a sparse attention mechanism to efficiently propagate information across nodes in a graph. We also discuss our adaptation of Spexphormer, which enhances scalability by avoiding message-passing neural network components while still capturing long-range dependencies. Section Method. In this section, we describe our method, which involves a two-phase training process. First, we train a model called the Attention Score Estimator Network. Its purpose is to estimate attention scores for a larger network. This model doesn't need to be highly accurate. It simply helps each node identify its most important neighbors. We then use the attention scores learned from this first network to create sparse interaction graphs for each layer in a second model, which we train with hyperparameter tuning to achieve optimal results. For the attention score estimator network, we use a width of either 4 or 8 and only one attention head during training. We adjust other hyperparameters to ensure the training process converges with reasonable accuracy, but we don't focus too much on optimizing this network since it only needs to identify important neighbors or edges with high attention scores. This network is trained with the same number of layers as the final model we aim to develop. Its narrow structure means it has significantly fewer parameters, resulting in lower memory and time complexity, making it more cost-effective to train. We only need to train this once for the number of layers we consider, as long as the training converges, even if the final model has many hyperparameters. In comparison to Spexphormer, we utilize a higher degree expander graph, ranging from 30 to 200, instead of the 6 typically used for most transductive graphs. Since most datasets we examine lack edge features, we implement a learnable embedding for each edge type, including graph edges, expander edges, and self-loops. We also introduce 2 minor modifications to the architecture and training process of this model, which we discuss later. Our experiments show that the low-width network effectively estimates the attention scores for a larger width network. Next, we address normalization. A smaller attention score does not always indicate that a neighbor's contribution to a node's new features is less significant. For instance, if the norm of one neighbor's features is much larger than another's, its overall contribution could be greater. While transformers usually apply layer normalization, they often skip this step after mapping input features to the value representations. We normalize the rows of the value matrix to ensure all nodes have the same vector sizes. In our experiments, normalizing to a size of 1 significantly reduced performance. However, by adding a learnable global scale, we maintain performance while making attention scores more interpretable. We also aim for sharper attention scores to encourage nodes to gather information from fewer neighbors. We achieve this by incorporating temperature into the attention mechanism, where we divide the logits by a temperature factor before applying softmax. Normal attention corresponds to a temperature of 1. A smaller temperature results in sharper attention scores. Instead of starting with a low temperature, we begin with 1 and gradually reduce it to 0.05 by the end of training. We set an initial phase for a specific number of epochs using a temperature of 1, allowing the model to slowly learn which neighbors are more important. After each epoch, we adjust the temperature based on a decay factor. To address the memory and time complexity of Spexphormer, we recognize that not all edges are equally important. Many edges have minimal impact on the final node embeddings, so reducing the number of edges can help with memory usage. A sparser attention pattern allows us to implement batching techniques for larger graphs. We analyze how effectively we can sparsify the model and determine the optimal factor for this process. For each layer, we select a fixed degree for each node and sample edges based on the attention scores from the estimator network during training or evaluation. We also employ reservoir sampling for faster edge selection. This method is more efficient than traditional sampling, especially when a few neighbors dominate the attention scores. We sample neighbors in parallel, which is GPU friendly, and we can optimize the process by forming a regular matrix for the attention scores. When it comes to batching, we start with a random subset of target nodes whose representations we will update. We sample neighbors for each target node and compute their representations based on the previous layer. This process allows us to efficiently handle the representations needed for each layer while ensuring that our approach selects neighbors based on their importance to the task. Finally, we address the efficiency of sparse matrix operations on GPUs. By normalizing the degree, we can reshape the key vectors, allowing for optimized matrix multiplications. This approach enhances the efficiency of our computations, making our method more effective overall. Section Summary. In this section, we describe our two-phase training method, which first involves training an attention score estimator network to identify important neighbors for each node, and then uses these learned attention scores to create sparse interaction graphs for a second model that serves as the final predictor. We also implement techniques such as variable temperature for sharper attention scores, reservoir sampling for efficient neighbor selection, and fixed node degree layers to optimize memory and computation during training and inference. Section: Theoretical Underpinnings. In this section, we first examine how well a network with a smaller hidden dimension can approximate a wider network. We define a wide network with a width of d. We find that we can create a narrower network for the query and key dimensions, which has a size proportional to the logarithm of the number of nodes divided by the square of a small error term, multiplied by d. This narrower network can produce attention scores that closely match those of the wider network, with only a small error. This reduction simplifies the most complex calculations, while other calculations scale linearly with the number of nodes. Although this isn't the model we use in practice, we explore scenarios in Section 4 where fully narrow networks can still yield accurate attention scores, supported by experiments showing that some datasets can be compressed effectively. We will also demonstrate that training a narrow network can indeed approximate attention scores well. Next, we analyze our sampling method for sparsification. Under certain conditions, we show that sampling about the logarithm of the number of nodes multiplied by the number of nodes divided by the square of the small error term is enough to create a matrix that closely resembles the original attention matrix, provided we can access its entries. While we can't access the original matrix directly, we do have attention scores from a narrow network. We demonstrate that if these scores do not significantly underestimate the original scores, the same sampling requirement applies. For our experimental results, we focus on how effectively the smaller network estimates the attention scores of a larger network. We conduct experiments on two smaller datasets, the actor and photo datasets, where we can train the full network at higher widths multiple times to understand the distribution of attention scores. We vary the hidden dimensions from 4 to 64 and train the network 100 times for each dimension. We analyze the attention score distributions for each node and calculate the energy distance, which helps us compare the scores across different hidden dimensions. We run these experiments in two scenarios, first with just graph edges, and then by adding additional edges. We note that the model might assign lower scores to certain edge types, making distributions appear more similar than they are, but it can still accurately identify which nodes should have higher attention scores. We compare our model's attention scores to a uniform distribution among neighbors and another distribution with values ranging from -8 to +8, as we clip the logits in our network at these values. Our findings show that even networks with a width of 4 provide much better estimates of attention scores than these baseline methods. In our extended analysis, we explore various aspects, including pairwise energy distances, the sharpness of attention scores across layers, and the precision and recall in estimating the larger network's attention scores using the smaller one. We also look at the sum of the top K attention scores and the impact of different edge types on learning representations. Our key insights are as follows. 1. Attention scores from a smaller network are effective estimators for those in a larger network. 2. Attention scores are smoother in the first layer and become sharper in later layers. 3. Scores in layers after the first are very similar to each other but differ from those in the first layer. 4. The sum of the top K attention scores is often less than 1 for many nodes, even for larger values of K, like 10. Section Summary. In this section, we explore the approximability of narrow networks in estimating attention scores from wider networks, demonstrating that a narrow network can achieve similar accuracy with significantly reduced dimensions. Our experiments reveal that smaller networks effectively estimate attention scores, with insights indicating that attention scores become sharper in deeper layers and that the sum of top attention scores remains low for many nodes. Section: Model Quality. In this section, we conduct experiments on 12 medium-sized graphs, which include 6 homophilic datasets: CS, Physics, Photo, Computer, Wiki CS, and OGBN Archive, and 6 heterophilic datasets: Minesweeper, Talokers, Roman Empire, Amazon Ratings, Questions, and Actor. For the CS, Physics, Photo, and Computer datasets, we randomly split the data into 60% for training, 20% for validation, and 20% for testing. For Wiki CS and OGBN Archive, we use the standard splits provided by the original sources. The Actor dataset is split into 50% for training, 25% for validation, and 25% for testing. We apply the standard splits for the other datasets as well. Our results are summarized in the tables for homophilic and heterophilic graphs. The EXPHORMER model we discuss refers to the attention mechanism without any MPNN components. Notably, we found that removing certain edges in the Roman Empire and Amazon Ratings datasets improved performance compared to just adding an expander layout. We successfully trained the full Spexphormer model on these medium-sized datasets. Our aim is to assess how much performance decreases when using two memory-efficient networks to estimate the original network. The results indicate that these networks can effectively estimate the original network, allowing us to scale Spexphormer to larger graph datasets. We compare the maximum memory required for the attention score estimator and final networks against the corresponding Spexphormer model. Next, we experiment with larger graph datasets, OGBN proteins, Amazon 2M, and POCIC. The results show that our model outperforms others despite memory limitations. We adhere to the standard data split for OGBN proteins and use specific splits for Amazon 2M and POCIC, with different ratios for training, validation, and testing. We note that our splits differ from those used in many other studies, making comparisons difficult. In all our experiments, we train the smaller network once and then use the learned attention scores from this network for the second one. We collect attention scores from the training step that achieve the highest validation accuracy. We utilize a subset of models as baselines, depending on the dataset type and model scalability, including GCN, GraphSage, GAT, and others. Most baseline numbers in our tables are sourced from previous works. For our ablation studies, we evaluate the impact of different model components. Spexphormer uniform samples uniformly from the augmented graph, which consistently performs worse than attention-based sampling, with the gap varying by dataset. Spexphormer Max selects edges with the highest attention scores instead of sampling, and this also shows slightly worse performance. We also test Spexphormer without temperature, using a constant temperature of 1, and Spexphormer without layer normalization, which sometimes worsens results. Overall, across the 4 datasets, both temperature and layer normalization appear to enhance the informativeness and sparsity of attention scores.